Today I'm going to give you sort of a practical tips session. This isn't anything new or innovative, but it may be something that someone else is doing that might help you in your research. This is really targeted towards people who are working on soft materials for the first time. So if you've been doing this for years and years and years, you can probably check your email now. I'm going to talk about the hardness of the experiments on soft materials. First off, you have to figure out what technique is best, and if you're using a traditional nanoindenter to do some of these materials, you may have to make certain compromises. And if you're working with biomaterials, everything has another layer of extra difficulty. In fluid, you may really need to work in fluid, but there are some things to think about as well. So this is basically a list of advice that I've learned from watching other people do experiments mostly. First off, you have to choose what tool you want to use. You need something that's sensitive to the regimes you're interested in. You need a high enough load sensitivity, and you need to be able to indent to depths that are relevant. Similarly, you also need to have lateral resolution. If you're going for something on the scale of a tensile test on a giant piece of bone, that's different from if you're trying to do an indent on a collagen fiber. You need different resolutions. If you're working on things on the millinewton, centinewton perhaps scale, the tools you want are more macroscopic. They're like rheometers or DMAs or various other tools. On the micro scale, shading into the nanoscale, come microindenters, nanoindenters, and AFM. And just a side note about microindentation, if you're using a nanoindenter, you may actually have a microindenter there too. A lot of companies will produce high load nanoindenters, which really go to tens of microns displacement, have almost Newton range. It's really a microindenter, but nano sounds cooler, and it's on a nanoindentation instrument, so we'll just call it a nanoindenter. Oh, heavens, sorry about that. The advantage of nanoindenters is manyfold. The advantage of microindenters for certain applications includes not ever having to think about the 5% rule, because if you've got a little bit of surface roughness and you're indenting many tens of microns or a millimeter into your material, it doesn't matter. Also, you can sort of ignore the surface adhesion effects. Moving on to another choice you might need to make, do you want to do time-dependent measurements or not? Most soft materials have something that is not purely elastoplastic, so you probably want to look at some sort of time-dependent measurement, whether you're engaging in the frequency regime or holding things. Now what's going on up here, this is, I just indented a nitrile glove. The creep versus relaxation here in both of these cases, the material is kind of moving away from the tip. For creep, you have a constant load, and so as the material is moving away, you move the tip down to keep the load constant. For stress relaxation, you have a constant displacement, so you fix the tip position, and then the material kind of shrinks away from it, lowering the load. One thing to note about dynamic testing in the frequency regime is you can look at a phase lag between different parts of the oscillation of the tip, and just make sure you're aware of what the convention is that your particular instrument manufacturer uses. Is a negative phase lag a positive number, or is it a negative number because it's a phase lag? I've actually seen this different on different instruments, and when it comes to AFM phase, there are instruments that center the phase at 90 degrees. There are some of them that center it at 0 degrees, and just be aware of what your instrument's convention is before you start publishing your data and wondering why it's negative. If you're working with biomaterials, everything gets a little bit more complicated, mostly because of the safety concerns. If you're like me and you started off as a kind of a hard materials physicist, and now you're suddenly doing biological projects, and everyone else in your research group does the hard materials, you may not be as familiar with the biosafety protocols as, say, a biologist coming in to do material science. So just kind of be aware that you may be surprised by some of the safety protocols you might have to think of. Your AFM tips might have to be disposed of as a biohazard depending on what you're doing. And you may need to educate your collaborators. One of the ways of getting, of avoiding some of the hassle of doing the biosafety protocols is to work out your experimental protocol on a bio-like sample. So for example, if you have a tissue which is probably a modulus of around 50 kilopascal, then figure out your experimental techniques on a hydrogel of a similar modulus because you don't have to worry about all the biosafety things. And it's cheaper in most cases than getting the frozen dead animal parts. If you need to fix your sample, for those of you who don't really do bio measurements, fixative is basically a preservative. You can think of it as mummifying your sample almost. This changes the mechanical properties. So it'll make your sample stiffer. But sometimes you can't study your sample without it being fixed for biosafety reasons. So in that case, you want to make sure to do controls all the time, because when you're fixing samples, let's use the example of some cells on a glass slide. You want to figure out the stiffness of the cells, you want to figure out how well they're attached, something like that. But they're fixed. So they're kind of coated in this thin layer of perfused glutaraldehyde or something, which has its own stiffness. So it's a good idea when you're fixing your cells on the slide to also fix some bare slides, and then you have these slides with the same amount of glutaraldehyde or whatever your fixative is on top of it. And then you can do a comparative study. Now this won't get rid of the effect completely because it's going to be different for depending on how much fixative is inside the cell, depending on how well you've done the fixation. Sometimes you put in too much fixative, sometimes you don't put in enough, and it changes. So just make a control every time and try to do a well-controlled experiment.
Put glutaraldehyde on the gel and see how it changes the stiffness.
That would be cool. I've never thought of putting it in a gel. I've thought, you know, glass slide because people, but yeah, people attach cells to gels too, right? So yeah, that would be interesting. That's a good idea. I like that. If you're working with something that's not fixed, you might need to keep it semi-alive, or at least in a biorelevant condition for temperatures and fluids. A lot of manufacturers will sell fluid cells, or you can just build your own. Since you're doing soft materials, you don't have to worry quite so much about the extra machine compliance, but just test to make sure. Also, life is gross. Biomaterials are often sticky and they leave residue on stuff, so you'll probably have to clean samples. Clean anything that touches your samples, including the tip. Now usually the tips don't get contaminated from indent to indent, although sometimes they do, and that's fun to clean up. But over time, especially if if you are indenting something, the residue might dry on the tip, and then you'll cross-contaminate it from sample to sample. You've got old dried residue. Make sure that when you're cleaning things up afterwards, you clean up everything that touches your sample. For example, it's not just your tip that touches the sample, it's also part of the indenter shaft that is in the fluid that might end up getting contaminated. Depending on how much you care about the contamination, you might have to clean quite a bit. Now, if you're like me, and apparently a lot of us seem to have this particular instrument in here, you're using a traditional nanoindenter to do soft materials, which adds some additional joy to the adventure. It's not really designed for this. They usually don't go deep enough, and the load resolution is not quite as fantastic as we'd like. As was alluded to as was alluded to earlier, they're load controlled. Usually, they'll tell you you can do displacement control, but here's what's really happening. In a load-controlled experiment, the tip is maintained at a constant force. It'll change settings in the instrument to keep the tip measuring a constant force. In a displacement-controlled experiment, which isn't really displacement controlled in this particular case, you try to keep the tip at a particular depth. But what's really happening is the instrument thinks the tip is wants to be at this depth. So in order to get the tip at this depth, I do some feedback to feed into the load control to keep it at the load corresponding to this depth. And this takes a long time and can affect your measurements. And sometimes this loop is just harder to tune. I've got some examples there of when I deliberately set the parameters wrong. Now, if you're doing if you're using an instrument like this where the optical microscope is offset from the tip, you want to see where you're doing your indents, and you also want to make sure not to whack your tip into protrusions on your sample. So there is something called the Kit Kat method, and I'm serious, I've seen this in papers. It uses the eponymous candy as a sample that you can make a nice deep indent with plastic deformation in, because if you've got a 100 micron radius of curvature condenspherical probe, you're not going to make a visible indent in a standard aluminum sample, which most people use for nanoindentation with traditional materials as their calibration. The idea is you make indents in something, then you look and see where they are, then you've got your alignment. So you have to see the indents. A lot of people choose, instead of chocolate, to use wax. I learned the hard way. Candle wax does stiffen after a few days, so you have to make new wax. But hey, wax is cheap. You just drip a few drops onto something. I've recently become even more enamored of crayon wax than candle wax because the colors seem to make the indent show up better. On the other hand, I was using a white candle, so maybe if I used a red candle, it would show up just as well. But crayon wax works too, in case you were wondering. If you're doing tipped optics calibrations with flat punches, it may be even harder to induce a nice visible deformation in something, depending on the size of your flat punch. So a technique that was pointed out to me was to use ink. You basically just make a puddle of ink by scribbling on a glass slide. Then you use your indenter tip exactly like a stamp. It's like a rubber stamp, except it's a sapphire stamp. And you just dip it into the ink, then indent somewhere else on the glass slide, and then there's your calibration. But be careful not to get this stuff into your sample. So moving on to how to prepare your samples, when I talk to people doing hard materials, I say sample preparation is probably the hardest part. For soft materials, sample preparation is the hardest part, and doing the experiment is the hardest part, and interpreting the data is the hardest part. But let's go into just sample preparation here. First things first, make sure it'll physically fit inside your instrument. Then you have to make sure that the sample will stay down, especially if it's in fluid. The surface tension of the fluid tends to suck the sample up to the top, and I was recently reminded of this last week when that happened to me. And keeping samples wet can be a challenge, especially if you're trying to keep your instrument dry, which you should, because electronics don't like being wet. To fit your sample inside your instrument, you have to think about what size the sample actually is. Just physically, you can't fit a horse femur inside your average AFM. A 15 millimeter sample disc is a pretty good lateral size if you're planning on putting it in some instrument that you know absolutely nothing about. A lot of nanoindenters have a nice big open stage though, so just look up the instrument you're going to use online or physically look at it and make sure your sample will physically fit in there. If you're doing AFM, you have an additional constraint because your AFM tip is limited by the Z range of the piezo that either the sample or the tip is mounted on. It's limited in the amount of surface height that it can handle variations in. Usually it's in the range of something like 15 microns. There are special bio-designed AFMs which can handle something like 40 microns, but that's a pretty typical size. You're interested here in the total feature height, so not the surface roughness. It's like the height of these mountains. You don't want anything tall enough that when you're scanning along the surface, you whack into it sideways because you can't lift the tip up high enough. My general advice is just always look at your sample under an optical microscope. Even if you're not doing things that you think are going to be really rough, even if you don't have like a pig heart or something that you're looking at, it's really surprisingly informative what a 20x objective on a cheap microscope will tell you about sample prep changes you need to make. For example, how good your polishing is, if you're polishing bone or you're polishing some other material. To actually mount your sample, the traditional nanoindenter way is with superglue. Fortunately, superglue has a lot of biomedical applications. They use it to glue people's arteries together, so it must be good. And it can handle water. One of the downsides of using glue-type things on porous samples is you have these pores at the bottom of your sample that the glue can wick up into, and so you end up with this glue-infused bottom of your sample. Now, if you've got something that's 3 inches thick, then the 10% rule from Nanoindentation quite comfortably applies, and you can completely ignore the glue at the bottom. But if you've got a really thin layer of tissue, say it's sectioned, you might have to think of a different way to hold your sample down so it doesn't end up completely covered in glue. There are different ways of embedding. The moral of the story is there are different ways you might have to think about. It's not as obvious as just glue it down.
What are those ways? I'm really interested.
Yeah,
in having this problem.
I've seen people embed things in epoxy, which is similar to the glue problem, but it's a bit more controlled because people they use the first section.
Yeah. And the epoxy can go over.
Yep, I've seen that happen. Yeah, one of the things that I kind of like doing is some sort of mechanical mounting.
From the sides,
yeah. The downside of that is you don't want it to be kind of curved, otherwise you're just measuring the bending.
But the other problem is that when you add fluid, the part that is not mechanically constrained is
Yep, and then it's under tension too. Yeah, I haven't come up with a perfect solution. If I did, I would be famous. But yeah.
There's a product called CellTac. It's made from barnacle protein or something. It's very expensive, but it really attaches cells to stuff.
I've heard good things about it. It seems to be similar to superglue in terms of its thickness and its tendency to wick up over the edges and things like that. But yeah, I've heard good things about that. I think mostly there's no good solution, but there are things that everybody does and just accepts that we're not at a really good place as far as that goes. Different gel embedding type things instead of epoxy, maybe PMMA maybe. Another problem with that, of course, it's always about getting over the top of your sample, which tends to happen. I've been interested in thinking about using like vacuum stages to hold things down, which is a bit of a problem in fluid because you'll just suck the fluid through. So that's my favorite, holding down thin hard material samples in air, but that won't work for fluid. Maybe some sort of pump, like a really large pump. Yeah.
You can also use, we've used for soft materials, coarse grit sandpaper, and you get it to adhere by laterally moving it, and so then it mechanically fixes, so that also helps.
Oh, that's cool.
So,
yeah, okay, so it's like,
the sandpaper is glued to a metal substrate or whatever underneath it.
Cool.
It's not foolproof, but.
That, I'm probably going to use that,
We use sandpaper on grips and mechanical testing of large soft specimens, right? And so we just sort of adapted that to compression and indentation.
I like that idea. Once you've physically got your sample on, we just started talking about working in fluid. Working in fluid may be absolutely necessary, and it usually makes things harder, but it could make your experiment more valid, so it might be worth it. First off, you have to make sure not to break your instrument because you can't do the experiment if your instrument is down. For nanoindenters, a lot of them have special fluid-compatible tips where, here's the actual diamond tip. You can't actually see it on this one. This is my 100-micron kind of spherical, so you could possibly see it if your eyes and my camera are good enough. They have a long shaft because what you're worried about here is this part, this round part here is inside the transducer. The tip is here. This doesn't give you much room in the fluid before you start dunking the transducer in the fluid. And so this longer shaft allows you to do that, but you also have capillary effects to worry about, so it's not just how thick that is there. Bear in mind, if you're working with fluid, if you're working with things like ethanol, that vapors can potentially deposit inside the electronics, maybe not immediately, but over time, and they can either, if they congeal into some sort of liquid, they can produce electrochemistry and leave corrosion on your electronics, which we actually had happen to one of our AFMs, or other bad things can happen. I have never heard of an AFM or nanoindenter exploding because of vapors, but it is not impossible. So clean your stuff. If you're working on an instrument that other people work on, or even just one that you have yourself, clean everything that's going to touch your sample before and after use. After, so that it's nice and clean afterwards, and before, on the assumption that everybody else working on the instrument is a slob, which may or may not be true, but it's at least a safe thing to do. So do you really want to work in fluid? Probably. It's important to keep the samples wet. It stops being a hydrogel if it's dry, right? So even if you dry and re-wet it, it still changes. If you think of something like bone that cracks when it dries out, then it changes. Also, it was mentioned that samples swell. I've seen an experiment where people were looking at swelling as a function of pH, and the sample was going up by microns over the course of 20 minutes. So you may have to pay attention to swelling and things drying out. There are different ways to work in fluid. One popular one is Petri dishes. I recommend for most instruments to use the lid of the Petri dish because it's shorter, and so it makes it easier not to whack that into the rest of the instrument. You also have to pick the right dish size. For some instruments, the little ones are better. For some instruments, the little ones will hit the transducer, so you have to use the larger ones. If you're working with an AFM, this is not so useful for nanoindenters. Sometimes it's just as simple as dropping some water on the sample and it'll just sit there. Or you can make a little hydrophobic barrier and make a tiny little dish of water. You need the cantilever to be completely immersed in fluid all the way up to the glass window that's at the top of the surface, because water and fluid have different indices of refraction, and you want to make sure that your laser is appropriately calibrated. For AFM, there are some additional restrictions on fluids. For nanoindentation, these bottom two apply as well. For AFM, you need to make sure your fluid is not opaque to the wavelength of the laser. It's usually infrared, sometimes red, so you're probably okay, but you don't want to attenuate your laser. The second one, I learned the hard way when I first started working on AFM in fluid. If you have something like what I was doing at the time was a lipid bilayer in liquid. You had the initial monolayer down there, and then the bilayer was being deposited. But the chunks of whatever the second part of the lipid bilayer was were floating around in the fluid, and they can occlude the laser beam and just block your signal entirely or change it. So be careful if you've got particulates in your fluid, because you may not be able to get a stable measurement. Now, for nanoindentation and fluid and AFM in fluid, you need to make sure, again, don't get things into the electronics. The reason I'm harping about this is we had some instruments go down because of this problem recently, so I was traumatized. And your fluid must not evaporate too quickly. So don't work in things with a really high vapor pressure unless you have a completely closed cell, because as the fluid level decreases, for AFM, the index of refraction that you're moving the tip through changes, but also suddenly the surface tension is different, the forces on the tip are different, you have different adhesion going on, and so it confuses your calibrations. For mechanical measurements in fluid, bear in mind that measurements of adhesion will be different in air. As you're moving the tip through the medium, there will be hydrodynamic drag. You may cause waves. There's surface tension at the top of the fluid, so you may end up accidentally thinking you're on the surface of the sample when you're really on the surface of the droplet as you're coming down. Additionally, if you approach the sample too quickly, then the fluid compresses, and so you may again falsely think you're on the sample. Finding the sample is sometimes tricky, especially if it does have a modulus really, really low and similar to compressed fluid. One thing to note about environmental conditions, if you've got wind, it can cause ripples in the fluid. This mostly matters for AFM tips where, especially if you've got something in the fluid. Now, in general, thermal stability is this huge problem, not just for fluid, but for everything. I found that an average sample takes maybe about 4 hours to sort of settle in the instrument. So if you have access to your own instrument, it might be good to start your samples and leave them in there overnight. But maybe your sample ages. Some samples stiffen with time. Some people's samples change with time or degrade. So just bear in mind the properties of your sample. And don't expect it to be as easy as a traditional experiment. If you're working in a group where you're the only bio person, you're the only soft materials person, everybody else works with hard materials, your experiment's probably going to take a little longer than everybody else's. There's nothing wrong with you. It's just that it's not as well developed of a field quite yet, which is what makes it exciting, because you have a chance to make a difference. And so don't panic if one other person once measured this instrument, and measured this sample with some similar technique, and you don't get the exact results. It's really sample prep dependent, and not everyone did it right. So ask other people who got it to work how they got it to work. There are a lot of clever people working on this. If you look around, you can see who else you can ask questions of and say, did it work for you? How'd you get it to work? How did you get your samples to sit down? And if you're working in a group that's been doing traditional materials for a long time, now you're doing soft materials, you may not have that expertise in-house, so you may have to go out and ask other people. But this is fun because you have the opportunity to come up with an incredibly genius idea, and then everybody else in the field will be tremendously grateful to you for having finally figured out how to stick samples down and that sort of thing. So it's exciting. If you want background, this is another way of asking other people how they do it, to read different books. This is kind of the classic textbook on basic nanoindentation, but for soft materials, I actually really like this purple book here. If you've got if you're a U of I student or employee or professor, we've got library access to this. I asked them to get this one. This one is really helpful if you look at specific chapters because it's got practical advice. This one has practical advice for harder materials. So with that, I will open up the floor to questions in general and in particular, if you like.